Thank you. I hope you can see it. Yeah.
Yeah. It's clear.
Okay. I will make fast also. This is the project that I'm managing now in Spain. And thank you, Chairman, for giving me the possibility to introduce it. Short introduction about the energy sector and the technology which we are developing in the project. So, as we know, the energy scenario is growing renewable energy, but also stable fossil fuel, which is not decreasing so much as it could be. So a solution for this could be carbon negative emissions, which are promoted also by the IPCC. An example of carbon negative emissions is represented by bioenergy with carbon capture and storage. How to do this? For example, by coupling chemical looping combustor with a gas turbine. Here we see the compressor. Compressed air passes through the air reactor of the chemical looping combustor, and it works like an externally fired gas turbine, because mainly this is air which reacts with the oxygen carrier, and let's say it consumes part of the oxygen, and then it expands directly in the turbo expander. So basically here we have nitrogen and a little oxygen expanding. And then the oxygen carrier is regenerated in the fuel reactor where it reacts with the fuel. The concept has been developed since the year 2005 by Dr. Wolf and Dr. Jan also, and it's also developed as a case study in the MIT with regenerated gas turbines. So why do we need another project on this? We need because we have barriers to the development of these technologies. This technology is TRL 7 more or less, but is not commercial. There are no commercial pressurized chemical looping plants at the moment. One is foreseen to be built in Canada, but it's not in place yet. So a problem could be the attrition rate of the oxygen carriers. This can produce dust. Then the kinetic aspects under pressurized condition and high temperature, because we need high temperature at the inlet of the gas turbine, let's say 1200 degrees minimum inlet temperature. So we have to use our reactor at quite high temperature and high pressure. We can range from 10 bars to 20 bars at the inlet of the gas turbine. So this is an issue also. And what about the total plant efficiency? There are studies in Aspen Plus and other simulation software that say that the electrical efficiency will decrease of 10%. So we have to see how this works and avoid it. Everybody knows what is chemical looping combustion, and the project I'm developing is with the Instituto de Carboquímica in Spain, Zaragoza. They are very experienced and highly cited researchers on chemical looping reactions. The facilities that we have is preparation of the fuel, reactivity in TGA, fluidized bed of different dimensions. Here we see, for example, different plants for different fuels: natural gas, liquid fuels, syngas, and solid fuels. The biggest plant they have is 50 kilowatts solid fuels. So we can say that these plants are more suitable for micro turbines than the big turbines, let's say so. The concept of the plant we have already introduced this, and the project is based on oxygen carrier preparation, batch tests, modeling, and continuous pilot tests with pyrolysis oils and other biofuels like syngas or biomethane or similar ones, mainly gaseous and liquid biofuels, not solid, not so much solid. So this is an example of the oxygen carrier. We see iron with alumina is produced. The alumina is a support for the iron, which is the oxygen carrier itself. As you know, iron is used also in the human body. If we think about hemoglobin, which is the main natural oxygen transporter in the human body. This is an example of a batch reactor, and our simulation platform works with the MFIX, which is a software developed by the National Energy Technology Laboratory, and ETL, which is a part of the DOE, and we use ParaView to see simulation results. Here is some results of the fluidized bed reactor, which is not in pressure. And here is average gas velocity and gas mass flow. And then we have the final products and the reaction rate of the oxygen carriers. Just to have an example, I hope it works. We have the fuel inside the reactor, and it is interesting at 3 minutes and about 20 seconds. Here we go. We see that the oxygen carrier is completely exhausted and the reduction cycle is finished. So we are able with this software to calculate the complete cycle duration for an oxygen carrier. We also made a simulation in collaboration with the Haas University, Huazhong University for Science and Technology, using Barracuda software. In this case, we tested syngas at pressurized conditions. So first, we calibrated the model with pressurized TGA data, and then we calculated the trend of hydrogen in the left and carbon monoxide along all the reactor. We also calculate how much was the cycle of the reaction. We see that after 72 seconds, more or less, the oxygen carrier is exhausted. So we come back to the original composition of syngas, which was assumed to be 50% volume hydrogen and 50% volume of carbon monoxide. Finally, these are the results. With our Barracuda test, we see that the behavior of carbon monoxide is influenced deeply by pressure, and for sure more than hydrogen. Hydrogen reaction is so fast that the influence of pressure is quite small, and also syngas behavior is exactly the sum of the behavior of hydrogen and carbon monoxide. These tests have allowed us to calculate what is the inventory in the fuel reactor, and we see that these results are opposite to the one of the pressurized TGA, because in the fluidized bed we have different heat transfer and temperature range. And we see that with the pressure condition, we need less inventory, and this was not expected in reality. Further check as a future development has to be performed with the pressurized reactor, but as I said, it's difficult to test experimentally these facilities because there are very few facilities. There are one in Korea, which is a fluidized bed reactor, And in the future, we think that maybe for gas turbine is more suitable to use a packed bed reactor. Why packed bed? Because maybe the packed bed could avoid dust going inside the turbine, so could protect more the turbine. So this could be a future development. We acknowledge the European Union to have funded this small project, which could be the starting of a new research cycle for this kind of reactors. And we have a project website and a repository where we publish all the new material and the new results that we find in the project. I thank you for the attention, and again for the possibility of presenting my project.
Thank you. It's a very interesting topic. And any questions from the audience? We still have 5 minutes. Maybe I would like to ask you one question. Okay. Yeah. I saw that in your PowerPoint that you mentioned you test the pressure with 20 bar, right?
Yeah.
20. And normally, like because we also engage in cool gasification, and normally the pressure is like within 40 to 60 bar, because we need to consider the utilization of the syngas for the chemical production. The 40 to 60 bar is better for the synthesis of the chemical, like a methanol, something like that. And how about the chemical looping? If you choose like a 20 bar, how can you connect the chemical looping part to the next, chemical production? I mean.
Yeah, thank you very much for this question, which is very interesting and very important. I also say to stay in contact because we can learn much from your experience also about reactors. And what I can say is that the pressure depends on the reactor configuration that you use. Let's say we don't know at the moment which is the best reactor to use. As I said, that maybe also packed bed could be nice instead of fluidized bed. But if we use the fluidized bed reactor, which is the one which is in place in our research center, is the one we are testing now. This is done with two coupled reactors. So we have the air reactor and the oxygen carrier reactor, which are both fluidized bed, but work in different regime. The air reactor works in fast fluidization regime, and the fuel reactor works in bubbling fluidization regime. And we have two pressure indexes, and they are very delicate because the two reactors they need to have a stable pressure inside, but this is very difficult to maintain at atmospheric conditions, because pressure, as you know, depends mainly from the height of the bed, because you have a pressure loss in the reactor, and also from the injection of the gas system, because you have a pressure loss also in that case. And given that the two reactors have two different fluidization regime, it's very difficult to control. I can foresee that if we increase the pressure again, 20, 30 can be the maximum for a gas turbine, and could be beneficial because it's very good to have high pressure. You produce much power if you have a high pressure. But it's difficult to control the reactor with this configuration. Maybe we find a better configuration and we can improve the results, but at the moment is a challenge to work with this high pressure. We hope to collaborate also with you to find a solution. Yeah.
Yeah. Anyway, thank you. Yeah. There's still a lot of work efforts we need to do. I mean, considering biomass chemical leaching, because you know, for biomass the cost is very high. The only way is like we commercialize with a large scale, and a lot of efforts is needed for like a connect the upstream and the downstream. Yeah, especially consider the pressure level. Okay. Anyway, thank you for your nice presentation. Okay, let's keep it up.